like 50 cents.
75 cents for 4 pages, 80 cents for 8.
Yeah, I think that's a bit of a rip.
Yeah, right.
By saying like, I don't
Well,
like
16
$8.
sides, right? 8 sheets.
13.
Still, that seems a little high.
I would be willing to say though
I was born after that.
either tappy. You're all right for now. But when class starts, I can't have any. Okay. And then I'm just like rocking beats in my head and I'm listening.
Finding time workshop.
I get that way when I'm tired, but my little brother is a tapper like
Yeah, like I could have done that last minute, but we ran out of time. And like if I had an extra half an hour, I would like nail everything.
like random.
Yeah, it's like a section. It's at 7.
You know how I live?
I think.
And you know where the end of highway
The underground lab. It's like what, 118 or something? Like that. There's an SPS meeting tonight.
5 miles. Like,
It's
if
a
you're
section.
7 I'm like,
But I also need to put my.
because I have a
Yeah, and I feel like my
until like
shirts
6:30,
are
so it's not. No. I'm in the middle. I have to come out at 6:30, so it's pretty sweet.
Oh,
I put in one.
I like 7
Are you in it? Thanks for David.
We have like
Am I? No. Oh gosh. Here comes the snow.
Wait, what?
Stories and parties.
Unless you're sick of it. Unless you're sick of it. Sick of it. Just because, like, you have a lot of, like, volunteer work to do. Like, essentially after the pledging or that, but, like, all the
What's that?
things around.
Yes, please.
So,
Oh, it's so rowdy. We need to keep it down. We have a guest, Mr. Vestal's sister, who's a senior at Wofford in physics major. Who's graduating from Wofford. So Dr. Welch and Dr. Lejeune at Wofford have used this book. Have you studied from the book?
Yeah, the PFR text?
Yes, ma'am.
Yeah, I really like it.
Good. Say hello to Dan and Dan from Dr. Welch and Dr. Lejeune. And actually, I knew Dr. Sally when he was graduating from UGA years ago. Not well, but I knew him before he was at Wofford. Okay, let's see. The human intellect is measured by things so that man's thought is not true of its own account, but is called true in virtue of its conformity with things. So truth in the mind is in the conformity of our ideas with reality, not the other way around. Okay, so in struggling through some of the work, I don't think today's homework was particularly difficult, but in some of the homework that you're struggling through, sometimes in some of the assignments, some of the problems will be more difficult than other ones, and there's lots of reason for that. Sometimes there will be problems that I may not expect most of the people to be able to get, but the struggle against some of these problems is well worth the time and effort. Who are we missing? Mr. Averett. Mr. Averett, how are you, sir?
Sorry, he came to your class.
Oh. What? Oh.
Calling you out.
He's probably there just sleeping. I just didn't notice.
Go ahead and take a seat, Mr. Averett. So, the struggle against some of these problems is an important part of learning. Excuse me just a second. I need to fix this camera a little bit. Okay. So just the struggle itself will hopefully be something that will be a useful experience from you if you go at it with the right attitude, right? Obviously, it could be depressing or demoralizing or something if you don't have the right attitude. But you have to realize you have to be patient. So, walking through the darkness sometimes is a good thing for you if you have the attitude that you're exploring things, you're finding stuff, and maybe the light will come on and you'll see all this stuff was there and you didn't see it before. But the stuff you did find will kind of make a lot more sense. But even if you don't find much on your own, just groping around that's really what physics is about if you become a professional at it. Most of the time you don't know what you're doing. 90% of the time you're dealing with stuff you don't know how it's going to turn out. And that's a difficult transition for students, graduate students, to make from coursework to research, and a lot of students have trouble with that step. They can do coursework great, but you put them off on their own and they don't know what to do anymore because they're not used to groping around and trying to find something that they're not even sure what's there. That's a very common problem. I had one student, he just never got the idea. He would keep coming in and he said, okay, I want you to tell me how my thesis is going to turn out. And I said, I really don't know. That's the point. Nobody knows. You're the only one. By the end of this, you'll be the world's expert in that one little subject. But he never did get it. So he went off. He got too frustrated. The other thing is, even if you if you do find something on your own, that's great because you learn that. And if you still struggle with it, at least you'll learn a few things that are important. One is how much you don't know. There's a lot you don't know. You don't even know how much you don't know, right? There's a lot you don't know. And to give you an example, I thought about handing out the written qualifying exams for you, to see what they're like. Yeah.
You should
4 or 5 years from now, if you're in graduate school, thinking of going on for your PhD, you'll be facing those. And even if you aren't going to be doing that, you'll see what other people will, and they'll give you an understanding of what it is, what people like the faculty here have gone through already. They've all been through this stuff, and there is a big gap there. There's no doubt about it. We put a lot of emphasis at Clemson and other places. It's in vogue now to talk about undergraduate research, which drives me nuts because y'all don't know enough to do any research yet in physics. You just don't know it. You could call it undergraduate research experience. That's a little better. It tones it down a little bit. And it's not just unfair to those people who have had a lot of training and who are now doing research. It's also unfair to you because you get in, you go to a professor, you say, I want to do my senior thesis with you, or something sooner, something earlier. Want to get involved in the lab. And it's nice at Clemson we have a graduate program, so you can get involved with research groups here. But you go in and you talk to the professor, and he says, well, okay, what do you know? Well, I've had freshman physics. Or maybe a little bit more, right? So he gives you something that's kind of simple and mundane, and the problem is you don't know how your little bit fits into the bigger picture because you don't know the bigger picture. And you start to get the impression that research is pretty dull, really boring, because it's very repetitive. You do the same thing over and over again, and it doesn't seem to make a lot of sense. And that's because you don't have the perspective that a graduate student might. Sees the bigger picture, and it's exciting to be doing this, but there's a lot of grunt work you got to go through to get from one place to the other. So it's good for you to know that, to understand that there's a lot of work there, and to be patient with yourself, and don't expect too much too soon of yourselves. So research experience for undergraduates is a good thing, but you have to put it in context. And so that, by the way, for those of you who might have summers open, you might consider applying to REU programs, they're called. Ms. Vestal, did you do an REU program?
Yeah, I did it at Baylor. I really enjoyed it.
Yeah. REU, so you go on Google REU and you'll find in physics departments all across the country, they'll have summer programs you can apply. Usually they're looking for somebody maybe who's rising junior, so a rising sophomore is probably maybe not going to make it, but a rising junior is just right. Maybe a rising senior. It's a good one too. Mr. Farmer went up to Fermi Lab this last summer and some other places. He wants to go to CERN next summer, I'll argue. So, Mr. Avery.
Yeah, you're talking about the research and stuff, right?
Yes.
Yeah, Kristen, Miss Brandenburg,
Yeah.
she was like,
She went to
Texas.
TAMU. No, she went to A&M, Texas A&M.
Yeah, Texas, yeah.
Not Texas. Texas is in Austin. Texas A&M is in College Station.
I don't
Two
know the
different
difference.
schools.
Okay, but yeah, she was like, she went there and it was like a lot of fun.
Yeah.
And like even they also took her like skydiving and whatnot.
Okay, well,
But I'm just saying in general.
We don't get to do that all the time.
The
but-
research part, she was like, it was a lot of fun. It was a good opportunity and whatnot.
It may be a lot of fun, but it's also a good learning experience, and there are a lot of things. I mean, they have organized activities and
Got
stuff.
like 6K off of it. I was like, dang.
Yeah, they give you some support.
Yeah.
And they also sometimes will send you to a meeting where there are other RU students at the end of the summer or in the fall where you get to present. Tell them what you did. Make a little poster or presentation on what you did. Kind of share that. It's a good experience. It gets you out of the classroom, but it builds on what you're learning in the classroom. So the classroom forms the foundation. So don't think that somehow you can get things out of order. These are all good things, but you got to take them in the right order. Good things come right in the right order. So, okay. So be patient with yourselves when you're struggling perhaps with some homework problems. Okay. So I wanted to go over a couple of force laws. We were doing force laws, and there were two that I wanted to discuss. So a force law is something that you're going to use in Newton's second law, what dp dt is equal to. So we did kinetic friction. Can somebody please remind us of the force law for kinetic friction? So I want a magnitude and direction for the force due to kinetic friction. So something is sliding over something else. There's two surfaces in contact. Imagine sandpaper or something. This one's.
It opposes the sliding, and it's mu of kinetic friction normal.
Yes, ma'am. Times the normal force. Right. Opposes sliding. So it's going to try to slow the thing down to stop the sliding. And its magnitude is mu k n, where n is the normal force that the body is pressing down onto the surface with. Could be the weight, because the normal force is balanced sometimes by the weight, but not always. It's not always equal to the weight, but it is proportional to n. So let's look at the dimensionality here. What is the dimensionality of force? It's a mass times acceleration, right? ml per t squared. What's the dimensionality of n?
MLT.
It's the same. It's a force. The normal force is a force. It's also a force. So what's the dimensionality of mu k? It's dimensionless. And its value is generally between 0 and 1. Usually the sliding friction is not as big as the normal force. Usually mu k is 0.3 or something like that. Depends a lot on the materials involved as well as other things. And this is an idealization, keep in mind. This is not going to give you a precise accounting of sliding friction, but it's a pretty good approximation. We're going to use it. Mechanical engineers would have a better accounting of kinetic friction than what we're going to use. We're idealizing it. Okay, static friction. So the thing has stopped moving. It's no longer sliding. What is the magnitude and direction of static friction?
What'd you say?
Opposite to all other forces.
Good. It's opposite to the net of the other forces, right? It opposes the other forces that want to make it slide. So opposes the net of other forces that are inducing a sliding motion. So whatever is necessary, so it's trying to oppose those. Just keep it from sliding. That's static friction. How about the magnitude? This one's a little tricky. It's not given. It doesn't have a fixed value like kinetic friction. It's not going to be like that.
Whatever's keeping it from sliding.
Yeah, whatever is necessary to keep it from sliding, except whatever is necessary to prevent sliding, except what?
Up to mu sub s unknown.
Yes, sir. It has a maximum value, a maximum amount of that static friction can achieve. So, except it must be less than or equal to μSN, again proportional to the normal force. But the static friction can be less than the normal force. Let's imagine we have a table and we have a block that's on the table, and it's horizontal. What are the forces acting on this block presently? Gravity is pulling it down. Normal force opposing the gravity. So in this case, the normal force is equal to mg, in this case only. And is there any friction? It's horizontal. So there's no friction. Static friction is 0. It's not μSN. It's 0. There's no need for it. Let's put the thing at an incline. Okay, so this is the downward gravity, and let's suppose that the angle of the incline is theta. Normal force, and a third force is static friction. We're just lifting the table slowly up. It's not yet sliding. Keep going, it'll start sliding, but if you just lift it a little bit, it won't slide. Which way is the static friction going in this? Yes, sir. Mr. Disharoon says up, this way. And how big is it? Well, whatever is necessary to oppose the other components of the force that are causing it to slide. So let's do, in this force diagram, I don't like components drawn into force diagrams. So I'd rather you have a separate diagram off to the side here where you're going to resolve components. Let's resolve the force of gravity into pieces which are perpendicular and parallel to the ramp. So there's a force which is perpendicular to the ramp due to gravity and a force which is parallel to the ramp due to gravity. Now, the angle of the ramp, the incline, is theta. Can you point to an angle in that little triangle over here? Is there no? Oh, wow, I didn't know I could do that. Wow. I've got to put it back.
I love when adults feel small.
Whoa, dang it. How did that happen? What did I do? All right. I'm learning all kinds of things about this. All right. So is there an angle inside of that triangle that is theta?
Would it be between mg and f of
Yes, sir.
f perpendicular?
Yeah, that's right. And if that's a little difficult for you to see, take time and study it because you're going to need to know these geometries like this. This is the angle theta right there. One way to say it is what is the angle if the ramp, if theta is put back to 0, the ramp is horizontal, then of course this angle comes back, this comes down here, and that angle would be 0. So it's the same angle as the angle of the ramp right there. Okay, given that then, what are the components here? What is the amount of F perpendicular to the ramp, and what is the amount of F parallel to the ramp? Well, you have the magnitude of the hypotenuse.
Use mg cosine theta.
And which goes where?
Cosine would be the height, or the f perpendicular.
The perpendicular part.
And then mg sine would be f parallel.
Okay. Now, let's consider the forces acting upon this mass perpendicular to the ramp. Does the force of static friction act perpendicular to the ramp at all?
No, because it's balanced out by the normal force.
Parallel to the ramp. So perpendicular to the ramp, we have the normal force is balanced by only part of the weight. So what is the magnitude of the normal force?
mg cosine theta.
Yes, sir. Okay. It's not mg, it's mg cosine theta, it depends on theta. Because, and I want a reason, always give me reasons, because, why?
Okay, that's the amount needed to balance out.
Right. Yeah, it's not accelerating perpendicular to the ramp, right? So there's no acceleration perpendicular to ramp, and which is, we're looking at the effect and deducing the cause. In other words, we look at the lack of acceleration and deduce that there is no cause of acceleration, right? We work backwards from the effect to the cause. Okay, so then having deduced in, now what is the magnitude of Fs?
mg sine.
Bingo. Very good. Why do we know that Fs is mg sine theta?
Because that's the amount, that's the net thing that's needed to balance out, since it's already out by the force normal, you got the mg sign, which is left, and blah, 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 and that's the net.
Yeah, you got it. Looking at the forces, the components of the forces acting in this direction, there's no acceleration. We're told that this block is stationary on the ramp. Remember that. It's not sliding. Therefore, there's no acceleration along the ramp. Therefore, the components in all directions, independent directions, balance out. So the force of static friction is balanced by the amount of the gravity that's acting down the ramp. That's not US in, is it? It's less than US in, because n is mg cosine theta. So this is going to be less than US in, which is US mg cosine theta. So it's actually less. But what if, now we keep increasing the angle. The force of static friction is increasing because the force pulling down the ramp is increasing because the angle is increasing. So the force of static friction has to be increasing to balance that. Until we get to what?
Until it's
mg sine of
perpendicular.
theta is greater than.
Exactly. We reach the limit. So the limit, the largest angle, the largest value of theta, where there is no sliding, okay, no sliding, that's when they equal each other. In other words, mg sine, and I'm going to put theta sub c, meaning the critical value where it's going to just about to slide. And so I need US mg cosine theta c. Okay, and now I can take out common factors. The mass is not zero. The acceleration due to gravity is not zero. So then I can say that I have a relationship involving the critical angle and the static coefficient. Right? The cotangent of the critical the tangent of the critical angle is equal to the static friction, coefficient of static friction. Okay, so that tells you a little bit, explains a little bit about static friction and kinetic friction. Very important to understand the distinction between the two. They're both idealizations, but these are the ones that we're going to use in this course, and they're actually pretty good. They're not bad descriptions of friction, but they have their limits. Okay, another force law is air resistance, or air drag. The force due to air resistance is proportional to the velocity, but in the opposite direction.
What's that little,
Gamma.
what's that used for? Just air resistance coefficient?
It's the it's the drag coefficient. So gamma is called the drag coefficient. It depends on the density of the air, the composition of the air. It depends on the shape of the body. Again, this is an idealization. It says that the drag is always proportional to the speed. So it's opposite to the velocity and proportional. So that double the speed, you double the drag force. Okay. Let's look at dimensional analysis. What is the dimensionality of the left-hand side?
ML to -2.
MLT and
Right. Mr. Disherud, how about
I got you.
the dimensionality of the velocity?
it's going to be L over T.
Good. So what is the dimensionality of gamma? Mr. Creer, you think you can figure that one?
LT to -1, MLT to it's T to the -3.
Yeah, almost. Not quite. It's the other way around. So it'd be MLT. It's the gamma is going to be the force divided by the velocity, right? And the force is MLT minus 2, and the velocity is LT minus 1. So it's MT minus 1. Okay. So that's the dimensionality of that drag coefficient. So unlike mu, which is dimensionless, this has dimension. And it depends on the shape of the body and all kinds of other things, temperature and composition of the air and stuff. Okay. So much for force laws. We're going to be moving on now. So you have force laws, and so we're going to be putting these together to do lots of interesting problems where things are going to be sliding and flying through the air and doing other stuff. gravity, friction, pulleys, ropes, a whole bunch of stuff. We're going to be doing a lot of these. So let's go back here to let's consider what we know from Newton's second law. And let's consider this in one dimension, so there's no vector here, just a component in one dimension. Let's suppose we take the case of no forces. So this is case 1 in one dimension, no forces. What kind of motion is present if we have no forces acting?
Constant.
Yes, ma'am? Ms. Shaven?
Uniform
Linear.
uniform.
Uniform linear.
Acceleration.
No, ma'am. It's not accelerating.
Translation.
Yeah, uniform linear translation. Right. ULT, translation, uniform linear translation. What happens in terms of the impetus? Mr. Fanning, what happens in terms of the impetus for a body which is sliding along it? There's icy, there's no friction, it's icy, just slides. What happens to the impetus?
It stays the same.
Yes, sir. So it just slides, keeps its same. The momentum is the same, the velocity remains the same as long as it remains in one piece and doesn't start spitting off pieces or something. It would just keep moving in uniform linear translation. Okay? So this equation here, dp dt is equal to 0, implies what about p? That p of t is a constant. It doesn't depend on time. So looking at the solution of the differential equation, we find that p is a constant. In other words, m times the velocity, dx dt, is a constant. So we're going to call this p0, meaning it's the momentum. So the velocity, mv, is equal to p naught. So the velocity is p naught over m. And so the velocity is dx dt, and that's equal to p naught over m. So now the derivative is a constant. What does that say about x of t? It has a constant slope. If we plot the graph, position versus time, Mr. Covington, if position versus time is constant slope, slope doesn't change, what does that say about the line, the shape of the curve?
Then it's just going to be like a number indicating a straight line across.
Right, yeah.
So, like 3 or something like that.
Right, indicating a constant slope. So we have a constant here plus p naught over m, and that constant has to do with the initial value of x. Right? This is the initial value. We could also write this in terms of the velocity, which is constant v naught t, x plus v naught t. So this describes uniform linear translation. Okay, notice that we have two initial conditions. And what are those initial conditions? The initial position and the initial velocity. And we have one differential equation. If I write it down all at once, x double dot is equal to 0. I wrote it first in terms of the momentum, but if we write it in terms of x and divide out the mass, x double dot is equal to 0. So what we have here is a differential equation with two initial conditions, and the solution is then what we wrote here. X of t is x naught plus v naught t. The two conditions should correspond to your experience, your intuition. If I'm going to launch a rocket, or a cannonball, I can determine where the cannon is. That's its initial position, and I can determine the angle of the muzzle, and I can determine the muzzle speed by how much I load in here, and the weight of the cannonball and all that stuff. So I can set those two things, but I can't set anything else. I can't set the acceleration or anything. That's determined by what happens by the forces acting on the cannonball. So I could do it indirectly by doing it on the moon instead of on the Earth or something. But in terms of what I can vary here on the Earth, I can set two initial conditions: initial location and initial velocity. Okay, so let's go to the next case then. Let's go to case 2. Oops. Oh man, crazy. Here. Let's go to case 2. So I want a constant force. I'm going to make a force now acting on the thing. But I'm going to make it a constant force, so the force does not change in time. And an example of that is gravity near the surface of the Earth. The force of gravity, we said, is mg down. So if I write this in terms of the height above the surface of the Earth, so y is equal to the height, then I get a differential equation that looks like that. Newton's second law looks like that. My double dot is minus mg. Force of gravity is negative because it's down. And I'm measuring y from the floor. So y is up. So y hat, in other words, is up. The force of gravity is mg. And in these coordinates, it would be down. Mg y hat, it's down. And the position is y times y hat. Okay, so this is if we're considering just vertical motion, this is Newton's law. It's governing this. Now let's consider that case. What happens in that case physically in terms of impetus? Suppose I take this thing and I release it. Does it have impetus to begin with? No. What happens? More impetus, right? There's a force acting downward, so it's going to increase its impetus. Does its impetus remain constant after it gets impetus, Miss Maul?
It should.
Sorry?
It does.
Well, let's see. So its velocity is proportional to its momentum. Does it continue to drop at the same speed, or does it get faster?
It should accelerate.
Right. So what does that say about the momentum? What is the conclusion about the momentum?
That it changes.
It's increasing, right? Yeah, so its impetus is increasing. The longer the force acts on it, the more impetus it's going to have in the downward direction. So the gravity is going to continue to give additional impetus as long as it acts on the body, which is as long as it's hanging around here, right? Now, Ms. Watson, what if I throw this up? Here's a challenge for you. I throw it up. All right, it comes back down. But what's going on at the beginning there? I throw it up. In what direction is the impetus?
The impetus is up.
It's up. And does it have constant impetus?
No.
It's
Slowing down.
Yeah. Gravity is pulling down on it, and it's draining impetus from the body until it gets right here. And then what happens, Mr. Jackson, at this point? Its highest point.
The force of gravity begins decelerating, and it stops accelerating one direction and starts accelerating the other.
Yeah, let's not talk about acceleration. I want it directly in terms of impetus. So what has happened to the impetus? Is there any impetus when it's at its highest? No, sir. No impetus. Right. It's stopped. It's been drained. What was initially vertical impetus has now been drained from it. And just for an instant, it's got no impetus. It's just hanging there. Now it starts to do what was done before. The gravity is continuing to pull. Gravity never stopped during this whole time. So now it's going to continue to pull down. It's going to give downward impetus to the body, and it starts to fall. So we should see this starts to accelerate downward. We should see that happening here. Okay. So let's divide out the masses here. Y double dot is minus g. That means the acceleration in the vertical direction is independent of mass. That's an interesting result. Does that seem to conform to your experience, that the acceleration doesn't depend on the mass? Yeah? If I take a feather and a bowling ball, which is going to hit the ground first?
The ball.
Yeah, why?
The air resistance.
Yeah, the air resistance. So we're neglecting the air resistance. If we get rid of the air resistance, we did that experiment on the moon, and it has been done. I think it was a feather and a hammer. One of the astronauts dropped them both, and they both landed at the same time on the moon. So if you get rid of the air resistance, then the acceleration is proportional to is the same for all bodies, because the mass is involved both in the impetus and the momentum, and also in the force. The force is proportional to the mass, and so is the momentum. So the effect cancels out. It's a weird thing. It doesn't have to be that way. Why is it that way is something we can learn more about later. Okay, so now, in terms of the shape, so we have some kind of shape here. Remember, these differential equations are always corresponding to some shape. I want you to imagine some kind of curve. Y of t versus t is a shape. And what does it mean y double dot is negative? Let's look up here. When we had the previous case, we had y double dot, x double dot was 0. X double dot is 0. It means a straight line. So remember the second derivative. The first derivative tells you the slope. The second derivative is the slope of the slope. That means how is the slope changing? Well, if the slope changes, then you have a curve. You don't have a straight line. So this is saying that the curvature of this is constant. And what kind of shape has constant curvature, has a constant second derivative? A parabola. Now, if I'm going to sketch this out, I'm going to have an inverted parabola. It's going to be upside down, right? The curvature is going to be upside down because g is negative g. Where am I going to start it? Well, I'm going to start it at its initial height, wherever it is when I toss it up. And it's got some initial velocity, which may be up. It might be 0. I could throw it down, so it starts with a negative velocity. So there are a number of curves I could draw here depending on the circumstances, but it'll look something like that. That would be corresponding to what I did with the remote. Tossed it up. So there's some initial height, y0. It has an initial velocity, v0, which is the slope of this curve, corresponds to the slope of the curve. And then it has a curvature, which is negative g. Okay, so the solution to this, and again, we're not studying the solution of differential equations, but you should be able to verify that this satisfies, all right, so I have initial condition. Let me write this way. Two initial conditions, which are the initial height and the initial velocity, as well as then the differential equation, second order differential equation. Second order because it involves the second derivative. Okay, and that's the solution. Now, you're not going to study the solutions of differential equations. We're going to do integration next term. We're not even going to, we could solve this easily with integration, but I'm not going to try to do that. But you should be able to do direct substitution. Just substitute this directly and verify by direct substitution that this satisfies the differential equation and the initial condition. Notice that Newton's law has become a differential equation. Newton's second law takes on the form of a differential equation here. Combined with the initial conditions, then what we have is a mathematical requirement which can be solved through mathematics to give us a solution for the motion of the body. There's no guessing here. If you know the initial position, you know the initial velocity, you know it. There's no guessing left. It can be determined. Now, so you can go backwards though. You should be able to just plug those in and verify. Okay. So, uniform linear acceleration corresponds to a parabola if I plot the position versus time. It's a parabola. If the acceleration is downward, then you get a negative curvature to it. Okay? All right, so suppose we had a cannon, and you're going to do this problem. Suppose we had a cannon here. Grass is green. Why not? There we go. So we have a cannon here like this, and the cannon is going to fire a projectile, has some muzzle velocity u, and some angle theta with respect to the horizontal. All right. Right? So I can control the incline, and I can control the muzzle velocity, and I launch this thing. And it's going to have a trajectory. Now this is going to be, again, no air resistance. We'll go back and try air resistance later. But remember, this process of abstraction, forming levels of abstraction, where we just consider just some aspect, some limited aspect or two, and just see what it does by itself. Then we go back in and think about what is concrete, what is real. Well, that's not real that there's no air resistance, around here. So add those things back in. But first we study these things in isolation. That's what the mind is capable of doing. All right. So here's what I want you to do for this sort of thing. I'm going to use this to describe a general approach. Actually, no. Hold on. I'm going to do a different one. So stop that. Let me just indicate here. I could draw a coordinate system. Let's call x and y. Actually, I want to put those. I don't want to put those there. I'm going to put them right where the cannonball begins. So let's assume that the cannon is kind of small. So here's the x and the y. Okay, and the cannonball flies off here. It has some initial velocity u, imparted by the cannon, and making an angle theta with the horizontal. Okay, so now I'm going to rely on the independence of motion in two directions. What are the forces acting on that cannonball when it's out here somewhere? No, and that's it. No air resistance. Very simple. Is there any horizontal force? Right. Mr. Tremblay, what happens to the impetus in the horizontal direction?
It's going to increase to a certain point and then decrease.
In this direction, horizontal direction. Is there any force acting after the cannonball, after it's been launched out of the cannon? After the.
So it's going to decrease.
Why would it decrease?
Okay, in the horizontal direction, I'll say the same.
Yeah, you got three choices. We got the other two first. So it's not going to decrease or increase because there's no force in the horizontal direction. There's nothing that's going to change its impetus in the horizontal direction. So what kind of motion in the horizontal direction? Uniform linear translation in the horizontal direction. Okay. Mr. Flanagan, how about in the vertical direction? There's a force acting. So what kind of motion will there be in the vertical direction?
A parabolic arc.
Yeah, in time. It'll look like that in time. It also, by coincidence, looks like that when we're plotting it. The trajectory in space will also look that way. Right. So, but if we're looking at it in time, it's going to be uniform linear acceleration, where the acceleration is downward. So we're combining those two things that we just did. In the horizontal direction is uniform linear translation, and the vertical direction is uniform acceleration. They're independent of each other, and so we can use the solutions that we got before. So x of t is equal to x naught plus v naught x, the component of x and the velocity in the x direction. Y of t is going to be y naught plus v naught, the component of the velocity in the y direction, minus 1/2 gt squared. Okay. Because the equations of motion are going to be mx double dot is 0, my double dot is minus mg. We've got x of 0 is x naught, and its initial velocity, we're going to study this here in just a second. Okay? So we just combine what we did before. They're independent. Nothing that connects them. Okay, so what we're left with here is finding the initial velocities in the two independent directions. We have a triangle here. U is the muzzle velocity. V0x is the component of the velocity in the x direction. V0y is the component of the muzzle velocity in the y direction. And theta is the angle that the muzzle makes with the horizontal. Mr. Hotchkiss, what are these x and y components of the initial velocity then?
What?
So I want to know V0x and V0y. So they form three sides of the triangle. The cannon shoots the cannonball out with that velocity at that direction. I want to know how horizontal is it and how vertical is it?
Like compared to theta, or
using theta also is going to dependent on you.
Wouldn't it be
It's just Straight trigonometry.
Yeah, I'm trying to think of it right now.
Yep.
It's not in the game.
You need not to be thinking about this anymore.
Yeah, I know. It's not in the game right now.
Okay.
So it'd be E naught x component would be u. Wouldn't it be cosine theta?
Good.
Okay, and then the other one would be u sine theta.
Good. So those are what go in here.
Huh?
And this is why you must know it.
Okay. All right. So when dealing with these problems in general approach to these motion problems, you're going to be doing lots of motion problems. Sometimes you're wanting to find the solution x of t, y of t that matches how is the body going to move. Sometimes you're going to want to know something else. In general, you're going to be looking either for displacements, so the unknowns, maybe displacements, or sometimes forces. Sometimes you don't know what the normal force is, you have to figure it out. Sometimes you don't know what the tension in the rope is, you have to figure it out. Okay, so let's take an example. Let's do this one. This is a good one. First, the very first thing is I want you to diagram the situation. Make a diagram of the bodies involved. So let's take an example of mass on an inclined plane here. Slides, doesn't roll. This is just sliding, no rolling. Right? We'll do rolling later, chapter 7. So that's it, right? You might be told that the angle of the incline is theta, and you might be told the mass of the body. Okay, so these are things that you would put in the diagram, just to indicate what it looks like. Okay. Number 2, I want a force diagram, separate. For every moving body, every moving body is going to have a force diagram. So for this one, I'm going to have gravity, and I might have the normal force. I might have friction. Might be kinetic friction if the thing is sliding. Suppose you kick it uphill, and it's sliding up. So it would have, in that case, kinetic friction back if it's sliding up, because the kinetic friction is tending to slow it down. Okay? I don't want resolution into components yet. I want you to tell me that there are 3 forces acting on this body, and not 4, and not 2, and not 1. Yes, sir, Mr. Flanagan.
If you were in a scenario where you were going to put air resistance on it, would it be a different, like a separate force from kinetic friction?
Say what?
If the block had air resistance.
Oh, if there were air resistance, it would be a different force in addition to the kinetic friction. Yes.
How would you draw it?
Oh, it would be opposite to the motion. So if it's sliding uphill, then I would draw it onto the center of mass of the thing, and the reason for that will be made clearer later. So this would be force of drag. So it'd be a fourth force. So I want, in the force diagram, I just show me the forces that are present. Don't start resolving them into components. Just show me that you know that there are 3 or 2 or 4 or something. Okay? That's that part. Number 3, step 3, choose a coordinate system and draw it. Oops, not a chord system, a coordinate system. So I'm going to pick, for this one, I'm going to pick a coordinate system that's rotated. It's going to be more convenient to have x go uphill and y be normal to the plane. That's going to be more convenient than having x and y be the usual horizontal and vertical. This is going to be easier. Why? Because the motion in the y direction is really simple. It doesn't do anything in the y direction. There's no acceleration in the y direction. The only thing that happens is in the x direction. So let me just pick my coordinate system to be in that direction, because that simplifies everything. Otherwise, if you have a coordinate system that's like this, then x and y are both changing, but here y doesn't change. So it really simplifies things. Okay, but that's your choice, and I want you to indicate to me, oh man, really? I want you to indicate to me what your choice is. You will have lots of freedom here to choose your own coordinate system, and what comes with freedom is experience learning what works and what doesn't work, right? So some things will be a lot easier than others.
So you're saying we should use like polar coordinates or something?
You can if you feel comfortable using polar coordinates. I'm happy with that, unless I specifically tell you not to. But I really don't think that'll work in this case. And mass on an inclined plane is
so
not.
Like in our homework, though, will there be
Chapter 8.
Or not this one.
Not this time.
Okay.
No polar coordinates here. Well, not until we get to rotation will we deal with polar coordinates. Okay, so then I want you to resolve the forces onto the coordinate system. In other words, I want you to write the Cartesian form of the forces. So the normal force, for example, is going to be in the y direction, and I don't know yet what it is. It's got some magnitude, but I do know it's in the y direction. The force of gravity, well, it's going to be x mg minus mg sine theta minus y hat mg cosine theta. That's what Mr. Hodgkiss showed us in the previous work back here, the x and y components. So that was like that for the velocity. So it's I did it up here for the ramp. No, I didn't do it. Where did I do it? Did it up here. Didn't I do it here somewhere? Okay. Anyway, let's resolve this force here. I'll extend this so I can show you this is force of gravity. Let me show you how this works. Okay. Here's the coordinate system, x hat and y hat. And I have the gravity is downward like this, and so I'm going to resolve it into two pieces. The part that's down, so this is mg, magnitude mg. This angle is theta again. So this piece here is mg cosine theta, and this piece is mg sine theta. And notice that gravity is both negative, that is downward in y hat, downward in x hat, so there's two negative signs here. Okay, so you're going to do that with all of the forces. You're going to resolve them onto the chosen coordinate system. Whatever you have present in your problem. Okay. Okay, and then at this point I want you to clearly identify the unknowns. I'm almost done here, so I'm not keeping it a little bit late. Yeah. Mr. Averett arrived late, so I'm going to keep him late. So we've got clearly identify the unknowns. What are the unknowns in this problem? It could be, for example, x of t is unknown. Y of t is easy. It's always 0. We might not know the normal force, so maybe the normal force is something we don't know, perhaps. But anyway, according to your problem, identify what it is that you're trying to find, right? I mean, that's before you proceed on. You want to know what it is that you've got to find. If you just start cranking equations around, you're going to get lost because you don't know where you're going. Okay, then write Newton's second law for each motion, and that means each component. In this case of the box sliding down the ramp, there's really only one, but you could start with y also, but that one's really kind of a trivial one. We know that that's not going to do anything, but you could write